Hi there! In this lecture, we're going to provide a walkthrough of the geometry processing pipeline, which is an essential tool within this course. To this end, we will look into goals of 3D and geometric computer vision systems and enumerate and look into common stages of geometry processing. We will cover scanning in detail in the next video. However, we will provide an overview of the registration steps and reconstruction and meshing. Within this course, we will not touch post-processing. However, we will return to that in the next videos. On the Friday tutorial and lab work, you will also consider 3D representations that occur in computer vision and computer graphics, including range images and point clouds, volumetric representations, and also surface meshes and implicit functions, and perhaps others. So let's start with discussing the geometry processing pipeline. What is the geometry processing pipeline? And what are basically the goals? Why do we need any kind of computer vision system to process data in 3D? Within this course, we will mostly be concerned about the two aspects of 3D and geometric computer vision systems. The first aspect focuses on constructing various geometry representations for multiple tasks from raw data, specifically from measurements such as range images, volumetric computed tomography, or magnetic resonance imaging, or a popular LiDAR technology, an acronym for light detection and ranging. Such pipelines usually involve numerous, possibly optional, steps, where one would convert between different data representations having different levels of abstraction. For the sake of this course, we will occasionally consider intermediate steps and look where one would be able to inject learnable stages, such as neural network-based semantic segmentation, into the pipeline. An example of conversion between different data representations would be to go from raw scanned points to a surface mesh and further to a parameterized patch layout, which is a desirable artifact in computer graphics or game design. Another and somewhat minor goal that we will seek would be to learn how to actually manipulate the obtained 3D geometry and perform at least the basic operations such as deformations or Boolean operations. Thus, what is the geometry processing pipeline? Well, in fact, it is a highly modular sequence of interrelated stages for manipulations with 3D data, commonly for 3D reconstruction and understanding. It provides a convenient concept of conversions between different 3D representations and data types. It typically is organized within a flow of going from lower level to higher level representations or properties. It also provides a convenient way of injecting other methods or models, as it is modular. A question arises, why do we even need to study an entire pipeline for 3D processing? In fact, most 3D scanners have accompanying software. Don't they already have it all? Well, in fact, most hardware systems for 3D acquisition come with standard or proprietary algorithms that cannot be customized and only provide a limited conversion or export options. Being able to intervene at any stage gives you a lot of flexibility, and being able to actually improve over the intermediate stages in the pipeline. It can also bring you significant performance gains in terms of the quality of the resulting 3D model, for example. Our goal for today would be to go over the standard reconstruction pipeline for 3D scanning. As we go, we will also touch two types of problems with existing techniques and ask questions about how these can be addressed by machine learning-based approaches. The first would be a low-level task, for example, those related to local surface properties, such as smoothing the noise or estimating normals, extracting curvature, and removing outliers. The other one would be connected to the high-level understanding, which would typically involve object semantics, such as part segmentation or instance segmentation. Let us enumerate common stages of geometry processing. This figure presents an overview of the 3D geometry acquisition setup. It commonly proceeds in several distinct stages, and we will overview each step in more extensive detail further. We start with 3D scanning, collecting data on the object's 3D shape and possibly its appearance, such as colors. Scanning is performed using either conventional devices, such as video cameras, or more sophisticated setups, such as depth sensors, computed tomography scanners, or LiDAR scanners. Importantly, for most objects, scanning results in multiple separate datasets, or sequences of observations where observations don't precisely match geometrically, as depicted in the figure, where 10 scans of the bunny are represented as range images, each in their respective coordinate system. Here comes the task of aligning the scans, or registration, where the goal would be to make all scans represent the scene in some unified global coordinate system. For instance, concerning the bunny scans, this amounts to searching for the depth sensor's viewpoints, bringing the range images to a specific global coordinate system. Having gathered the point measurements, one commonly extracts a surface-based representation of the 3D shape. While this surface-based representation is frequently a triangular or a quad mesh, recently, effective ways of representing 3D objects using higher-level constructs, such as parametric boundary representations or shape programs, have been emerged. Specifically, it became possible to actually extract such representations from raw scanned data. Several post-processing steps are commonly desirable, typically amounting to mesh and to optimization, such as smoothing, quadrangulation, or compression. In this video, we will demonstrate the actual scanning process for the task of reconstructing a skull of a prehistoric animal, in this case a coyote. In this case, the technician was actually able to perform a high-quality reconstruction with the aid of quite a number of manual work. The process starts with placing the object on a particular pose and scanning using a particular scanner. In this case, this is a structured light scanner that generates what is called the RGBD sequence of frames that are further stored in the memory of a computer. One may see that the scanning process is typically dependent on the object to be scanned. For example, it will be very challenging to scan a room of a large object such as a vehicle using such kind of a device. Scanning data are typically represented as 3D point clouds or depth images. As you can see, that scans are initially very noisy and contain large numbers of outliers. Additionally, they are contaminated with background, such as the support structures used to hold the actual skull. Therefore, the technician removes the background and the scans of the support structures to just arrive at the clean version of the object. Because the data that was acquired contains multiple sequences, we are arriving at a series of partial 3D scans, each made in its own coordinate system. Aligning scans is performed by selecting correspondences between pairs of points on the partial scans, and then an alignment algorithm actually registers the scan data as closely as possible. After the alignment has been performed, the fused point cloud, which now consists of millions of points, is being fed into the mesh reconstructor pipeline. The reconstructor pipeline integrates the scans into a large mesh. Because of the noise present in the scan, the mesh can be very imprecise and noisy as well, and may underrepresent certain structures of the object. To improve the mesh, the artist has chosen to manually smooth particular parts of the mesh. When the geometry is complete, it is painted with textures. This can be subsequently used for an application, in this case, measurement of a particular parts of the skull. To recap, the standard geometry pipeline for 3D scanning proceeds in a number of higher-level stages, where scanning itself is succeeded by registration, then reconstruction, and then post-processing, going from lower level to generally higher level representations. It allows for naturally allows for modularity, or extension and injection of different stages. Let us only briefly mention what is going on within the 3D scanning pipeline. You will have an entire lecture devoted to 3D scanning technologies. 3D scanning is the process of analyzing a real-world object or environment to collect data on its shape, meaning the geometry, and appearance, meaning color or texture. Many technologies exist for 3D scanning that are either contact or non-contact. For example, a contact technology would be a coordinate measurement machine, which physically scans all of the points on the surface of the object, while an optical technology might be using a photo camera to obtain images of the object. Additionally, some of the technologies are able to actually see inside the object, such as the computer tomography, which is able to reconstruct the internal structure of the object, not only the visible surface. We will not consider the 3D scanning pipeline in detail. Instead, we will assume that depth images or range scans are available for us, and we'll focus on the next steps. During the next week, we will provide more information about depth acquisition. Instead, we will consider registration in greater detail. Recall the video of the skull reconstruction. Within the video, it was necessary for an artist to align the range images of a skull by selecting correspondences and running an alignment algorithm to actually bring these images into the same coordinate system. That is, to align the images to one another. Turns out this is a necessary step in a lot of computer vision and geometry processing applications. In fact, what we're just about to consider is one of the key problems in computer vision, given a three-dimensional data, M1, in a sensor coordinate system, which describes a data shape, and a different model shape, M2. The goal is to estimate the optimal rotation and translation that aligns or registers the model shape and the data shape, minimizing the distance between the shapes. This would allow, for example, to determine the equivalence of the shapes by a simple mean square distance metric. For our context, however, we will only use the registration step to align the measurements. So, the registration is based on an assumption that when scanning shapes using high accuracy non-contact measurement devices or by shallow depths of field, uncertainty in different sensed points does not vary by much. So the scans are noisy but not too noisy. However, as you have seen in the previous video, the situation may be wildly different when scanning with noisy sensors which contain a lot of outliers and scattered points. For the purposes of our application to 3D reconstruction, we would like our registration method to be used with a point set representation of geometric data. However, as we will see further, a similar method will be possible to use with polylines, implicit curves, parametric curves, triangular sets or meshes, implicit surfaces, or parametric surfaces, so quite a number of different data modalities. Typically for practice, it is convenient to distinguish between global registration, that is, alignment of 3D shapes in arbitrary initial positions, and local registration, that assumes that the transformation that we are looking for is comparatively small in some sense. Typically, we're having multiple scans from M1 through Mn, and require finding a number of registration transformations. In this case, the model shape is the first shape, while other shapes are repositioned with respect to the model shape. The registration algorithm that we will be considering relies on the ability to compute the closest point on a geometric shape to a given point. If we have achieved this, then the iterative closest point, or ICP, algorithm can be used and described in terms of abstract geometric shapes, whose internal representation must be known to execute the algorithm. One question remains is how many points are the various minimum that we need to define a unique rigid transformation. For example, 2 points determine a line segment, and any rotation around that line segment will preserve those points. However, a set of 3 points will suffice, and will uniquely determine a transformation as long as it has no symmetries. Let P and Q define points on M1 and M2 respectively. Our goal will be to find the rotation matrix R and translation vector T that maps each point P to its respective corresponding point Q. Intuitively, if you already have the correct exact correspondences between P and Q, then your problem is the least squares estimate. You should estimate the rotation matrix and the translation vector, which can be solved by basically applying standard machinery and minimizing the least squares error. However, if you don't have the right correspondences, the ICP theorem states that you can still make progress by just computing the projections from points on the first shape to their closest points on the second shape. However, the algorithm will converge to the correct solution only if the starting points are close enough. Specifically, the ICP theorem states that the iterative closest point algorithm always converges monotonically to a local minimum with respect to the main square distance objective function. The basic ICP algorithm proceeds in 6 stages. First, we select, for example, 1,000 random points on the shape. Then we match these points to samples on the other scan, by using any data structure for approximate nearest neighbor finding, such as a KD tree, which will be discussed in subsequent lectures, or possibly directly computing Euclidean distance between each pair of correspondences. Then we can assign weights to the corresponding pairs appropriately, and possibly reject certain pairs, based on looking at each pair individually or considering the entire set of pairs. The commonly used error function is the basic mean-square difference between the transformed point from Q from P and the original point from Q. Then we basically minimize the error metric using gradient descent, for example. Variants of ICP vary by performing each of these steps a bit differently. For example, for the selection of points, the following strategies have been proposed. One can either always select all available points, subsample them uniformly or randomly, select points with high intensity gradient, or select points in different shapes differently. Another variant of ICP considers aligning not points to points, but points to planes by finding a nearest neighbor that lies somewhere in between the 2 points. This can be useful, for example, for aligning a point cloud to a mesh or a depth image to a parametric surface. Let us consider the algorithm in action. In this example, the original model shape to be aligned to is a point cloud sampled from a mesh of a bunny. The data shape, that is the shape that we're aligning the model shape to, is simply a copy of this original model shape. In reality, naturally, the data shape will never be a copy of the model shape, but will contain different measurements. The difference between the shapes is assigned manually by dragging the data shape away from the model shape by a small amount of space. Then, when the registration algorithm starts working, it quickly finds iterative correspondences between the pairs of points in the model and the data shapes. Note how the algorithm is able to quickly converge within a few iterations, almost precisely. The second demonstration illustrates aligning a depth map to a point cloud, which is a common task when we only have access to one particular view of the object, instead of the entire set of measurements. The difference in this situation is that the depth map is comparatively more continuous compared to a point cloud, which consists of discrete points. Still, ICP is able to perform robustly when rotating or displacing a point cloud from a depth map. To illustrate limitations of ICP, we will consider a different video, which aims to demonstrate a variant of ICP called GoICP. When a random point cloud is selected and the random pose is assigned to the data shape, the algorithm performs robustly as expected, just like previously. However, when we are registering a point cloud to an entire shape from a random pose, then the algorithm commonly gets stuck in the local minimum. When this is the case, the optimal alignment or an ideal alignment is difficult to achieve, and some displacement or misalignment will occur. Multiple invocations of the algorithm are necessary to achieve more optimal alignment, which can be made to perform better at the cost of an increased runtime. Another limitation is the existence of noise, which inevitably occurs in real-world scans. So this illustrates that aligning shapes using ICP when noise or outliers are present, and when the transformation that we seek is arbitrary, may result in a suboptimal or even a failed alignment. This slide enumerates the links to the original ICP paper along with the commonly used improvements and also a method for global registration. We encourage you to watch the video by Vlad and Colton on the recent paper on fast global registration. Registration might need to be non-rigid, as the range scans are usually warped due to sensor imperfections, such as spherical lenses, or non-rigid nature of registered objects, such as cloth. This, however, matters only for high-quality registration, not for finding coarse alignments. Additionally, even the direct ground truth for assessing the quality of the registration might not be available. One of the possible ways forward might be to leverage data-driven methods. For a set of objects, we could obtain a collection of warped scans for each object, and then learn an alignment or a dewarping transformation. A related and generally more difficult problem that receives a lot of attention recently is the non-rigid reconstruction. Let us further consider the 3D reconstruction step. So as you know now, 3D scanning commonly results in millions, if not billions, of 3D point measurements of a specific object. The goal of reconstruction is to arrive at a continuous representation of the underlying surface. In this slide, within a cultural heritage preservation context, two examples demonstrate huge scans consisting of billions of data points that have been transformed to high-quality triangular meshes with millions of triangular faces. An additional challenge in this context is that the scans represent free-form shapes, as compared to human-made shapes, where more robust priors are known, such as the flat surfaces or cylindrical surfaces, and that are commonly easier to fit. The definition of the reconstruction problem sounds like this. Having a partial information of an unknown surface, the goal is to construct, to the extent possible, a compact representation of the surface. One of the pioneering works in this direction was the work by Hoppe et al. In 1992. In this course, the information of an unknown surface that we have available would be multiple viewpoint and range data, so measurements lying on the surface of the object. Let us proceed to defining what the surface actually is. So, the surface is a compact, connected, orientable 2D manifold, possibly with boundary embedded in 3D. Typically, it is convenient to distinguish between closed surface, which is a surface without any boundary, and a bordered surface, which has a non-empty boundary. We will additionally look at simplicial surfaces which has a piecewise linear structure with triangular faces. So formally, the goal would be given examples x1 through xn, which lie on or near an unknown surface M, to recover an M' which approximates this original surface M. Recall that stitching or reconstruction of 3D scans, as performed on a registered 3D shape, where all range images or depth images have been brought to a single coordinate system and now represent a denser point cloud. The result is typically a triangular mesh. Typical inputs to this process may vary depending on how the 3D measurements are viewed. For instance, if the point set comes as a completely unstructured 3D point cloud, then it might be convenient to consider them just as a set of 3D points that are irregularly spaced. Commonly, to obtain a more robust 3D reconstruction, we will have to orient the surface. And to do that, we will have to estimate the orientation of each individual point. Specifically, we will have to estimate per-point normals. However, another input option might be that the normals come from the range scans, because these depict particular views of the object by the camera or a depth sensor. Because the camera views the object from a particular direction and is located outside the object, we are able to actually obtain estimates of point orientations automatically. The simplest way to obtain a mesh from points would be to basically connect nearby points by edges, ensuring a coherent structure of the mesh. To do this, we connect points by triangles, and this ensures that we exactly interpolate every single point, but can be bad for a noisy or a misaligned data and also needs to fill in holes or non-manifold structures in the mesh, generally meaning a poor or unusable mesh, or requiring, for example, a mesh repair. One important practical case of explicit reconstruction emerges if we view a range image as a mesh. A range image is a two-dimensional image composed of pixels, where each pixel stores depth value corresponding to a particular point in the scene. Range images are one of the most common modalities in 3D computer vision and occur in multiple view reconstruction, structured light scanning, infrared scanning, and other techniques. In the slide, you see the depth image in pseudo-color, with far points colored blue and close points colored red. If one views a local fragment of the depth image, it is nothing more but a 2D structured array of 3D vertices. So this means that one may connect close enough vertices by creating edges in horizontal and vertical directions, resulting in a rectangular graph. To further ensure the triangular mesh, one may connect every vertex to its neighbors on the diagonal of each cell. This leads to a particular connectivity pattern known as 4.8 Leaf styling or a 4-8 mesh. One may observe 4-8 meshes obtained using such a technique at low and high resolutions, respectively, along with the original range images in pseudo-color. Higher resolution depth images lead to significantly higher resolution surfaces. The goal of an implicit reconstruction is significantly different. We start with a set of range scans, but remove the existing connectivity, if any, between the adjacent vertices. Our goal will be to basically fit a function, only approximating the input points. If we succeed, this will lead to a watertight manifold results by construction. This machinery assumes there exists a function which maps points in R3 to a real line, with values greater than 0 outside the shape and lower than 0 inside the shape. Such a function is often called the sign distance function of this particular shape. The zero level set of this function is the set of 3D locations which corresponds to the surface of the object. One of the key ingredients in defining the sign distance function is to associate an oriented plane with each of the data points. So these tangent planes serve as local linear approximations to the surface. It is relatively simple to construct the tangent planes. However, the selection of their consistent orientation is one of the major obstacles. Normals, if available, will help to distinguish between inside and outside. Moreover, tangent planes do not directly define the surface, and their union may have a complicated non-manifold structure. However, we will use tangent planes to define the SDF, assigned distance function, to the surface. Consider a point x in the vicinity of the surface. Our goal will be to estimate f of x, the distance to the surface. So we will have to compute a sine distance function to the tangent plane of the closest point. This function will be discontinuous at certain points. The discontinuities result from the implicit partitioning of space into regions within which a single tangent plane is used to define the sine distance function. The original paper by Hoppe computes the tangent planes a little bit differently, but the consequences remain the same. To circumvent this problem, we would like to find a function f which implicitly defines the surface M and satisfies the equation f of p sub I equals 0. Here, p sub I are points lying on the surface. Our core assumption will be that they interpret the function f as smooth. One issue, however, is that the trivial solution is very easy to obtain, and the trivial solution is that f is 0 everywhere, which is of course not useful. To avoid that, we add off-surface points to the input data, giving them non-zero values. This gives a more useful interpolation problem where f of p sub I plus epsilon n sub I should be equal to epsilon, or minus epsilon if we're inside the surface. Off-surface points may be assigned either side of the surface, as illustrated in the figure. Experience has shown that it is better to augment a data point with two off-surface points on both sides of the surface. However, there still remains the problem of generating the off-surface points and the corresponding distance values, typically because we are only having a rough estimate of the normals, or are not provided the normals whatsoever. Given a set of zero-valued surface points and non-zero off-surface points, we now have a scattered data interpolation problem. So we want to approximate the sine distance function by an interpolant f of x. This function is a particular example of a radial basis function. Basis functions phi is a real valued function defined on the positive area, the positive side of the real line, usually unbounded and of non-zero compact support. In this context, the points c sub I are referred to as the centers of the RBF. So, popular choices for this basis function phi include splines and the Gaussian function. One can see that it is more likely to achieve more uniform reconstructions compared to non-manifold or non-uniform meshes obtained using explicit reconstruction methods. Surface reconstruction aims to create a surface representation from sparse input points. It can be either implicit or explicit. Explicit reconstruction aims to directly create connectivity by linking close points together or utilizing a 4-8 connectivity. The implicit reconstruction, on the contrast, aims to recover a sine distance function, or SDF, which is negative inside the shape and positive outside the shape, and then extract the level set. We will consider a state-of-the-art reconstruction algorithm called the Poisson surface reconstruction in greater detail in Lecture 6. Having obtained a zero-level set of an implicit surface, or having fitted the implicit surface by estimating the SDF, our goal will be now to actually extract the discretized representation of the surface for further use, for example within a computer graphics or other application. This process is referred to as meshing. The conversion from an implicit or volumetric representation to a triangular mesh, the so-called isosurface extraction, occurs, for example, in constructive solid geometry modeling, and in medical applications, for example, to extract the skull surface from a computed tomography head scan. The de facto standard algorithm for isosurface extraction is Marcin-Q's algorithm by Lorison and Klein from as early as 1987. So we would like to compute a manifold mesh of the level set of an estimated SDF. Formally, a mesh is a subdivision of a continuous geometric space into discrete geometric and topological cells. Often we seek to construct a simplicial surface, which is a surface made of piecewise linear elements, that is, triangles. So meshing is the process of converting between an implicit surface and a simplicial structured surface. We will start with considering a two-dimensional formulation. The dashed line represents the true surface as captured by the SDF. The red area outside the shape represents the positive values of the implicit sign distance function, while the green area represents the negative values. We will start with discretizing the sign distance function into two areas, one where it takes values greater than 0 and another where it takes values lower than 0. To perform this, we define a regular grid and compute values of the implicit function, obtaining effectively discrete distance field measurements. The real surface will therefore be an approximation of the actual zero-level set of the SDF. Our goal is to approximate an implicit surface with a mesh. However, computing all of its roots that correspond to the zero-level set is computationally expensive and requires root-finding methods. For each square cell that is intersected by the isosurface, in terms of the scalar field f, this means that the sign of f differs at the grid edges endpoints. A surface patch will be generated based on local criteria. The collection of all these small pieces eventually yields a polyline and, in 3D, a triangular mesh approximation of the complete isosurface. In 2D, 16 different configurations may exist that are determined by the different variants of the sign combinations in all cell endpoints. However, they decompose to only 4 equivalence classes, differing by rotation, reflection, or inversion. For example, class 1 represents a cell where the function is positive or negative in all 4 of the endpoints. Class 2 represents a case where the function is positive or negative only in one of those endpoints, and so on. Finally, having established the equivalence class, one can determine the intersection point by linear interpolation of the distance values at the edge's endpoints. In the figures on the side, the black lines denote the piecewise linear approximation of the target isosurface, This last case is ambiguous and can lead to two different possible configurations. The resulting sample points of each cell are then connected by a polyline to a surface patch based on a triangulation lookup table holding all possible configurations of edge intersections. So our goal will be to pick consistent orientation to avoid problems with the resulting mesh. In 3D, one would load 4 layers of the grid into memory and create a cube whose vertices lie on the 2 middle layers. We'll further classify the vertices of the cube according to the implicit function, inside, outside, or on the surface. It is interesting to note that each cell of the discrete distance field is processed separately, thereby allowing for trivial parallelization. Since the possible combinatorial configurations are determined by the signs of the cell's corners, their number, and hence the size of the table, is 2 to the power of 8, which is 256. So there exist 256 different configurations of signs in 3D, and different corners of this 3D cell. The 15 base configurations of the Martian cube's triangulation table are presented in the slide. The other 241 Ks can be found by rotation, reflection, or inversion. In this video, Martian cube's method is demonstrated first at low resolution 3 by 3 by 3 grid, aiming to extract the sphere from the SDF values defined in cell endpoints. Further, it is demonstrated at much higher resolution. In the end, while the result looks visually good, its structure suffers from a number of artifacts, which we will briefly describe. Isosurfaces extracted from binary segmented volume data suffer from aliasing and staircase artifacts. The human visual system is very sensitive to such discontinuities, since they normally represent salient visual cues for detection or classification of various objects. The standard Martian cube's algorithm leads to severe alias artifacts near sharp geometric features and elsewhere. We will only briefly mention the possible post-processing scenarios. The post-processing algorithms that are executed on the resulting triangular meshes are highly application dependent. For example, partitioning the surface into quadrangle rather than triangular tiles is a common requirement in computer graphics, where such quad tilings are amenable to a variety of subsequent applications due to their tensor product nature, such as B-spline fitting, simulation, texture atlasing, and rendering with highly detailed modulation maps. Converting a triangular meshes into a quadrangle meshes is known as quad-dominant remeshing or quadrangulation. Mesh smoothing is a fundamental tool in geometry processing, aiming to construct smooth functions defined on a mesh that can be flexibly chosen to describe vertex positions, texture coordinates, or vertex displacements. The smoothing techniques can be used for mesh parametrization, remeshing, hole filling, and mesh deformation. Mesh simplification and approximation transform a given polygonal mesh into another mesh with fewer faces, edges, and vertices. There are many applications for simplification and approximation, where they can be used to adjust the complexity of a geometric dataset to adjust to computers with varying computing performance.